Okay, good day, class. Good morning. All right, so today we are going to continue 6.1.3.5 scalar product. Okay, before this we have learned how to multiply a vector by a scalar. All right, so by using this concept, we have the ratio theorem. The formula to find the position vector of the point that divide AB internally and externally. Right, these two are important formula, right? Okay, so today we will see 3.1.3 6.1.3.5 scalar product. All right, so what is scalar product? Okay, so let's start with angle between two lines. All right, so let's say if I have two straight lines intersect each other like this, so we will have two angles between these two lines. So it means that it can be alpha or 180 minus alpha, right? Alpha is the angle between these two lines. 180 minus alpha also the angle between these two lines, right? So there will be two angles between two lines. But the angle between two vectors, which is theta, however, is defined uniquely, means only one. All right, not like straight line. Straight line we can have two. Okay, straight line we can have two possible angles. But for vectors, the angle between the two vectors is defined uniquely, means only one. All right, cannot have two. So which one is the angle that we want? That is the angle between two vectors. So it is the angle between their direction when the line representing them, means the line representing the vector, both converge to a point or both diverge from a point. So it means that the arrow, we will look at the arrow of the vectors. The direction is very important. All right, so it can be both vectors converge to a point. So if this happened, then this is the angle between these two vectors. Or two angles diverge from a point, also can. So we also can consider this one as the angle between two lines. In some cases, one of the line may have to produce in order to mark the correct angle. All right, produce means like this lah. All right, let's say I have one vector E going this direction, one vector F going this direction. All right, so if before this dash line, E and F, you see their arrow, they are not converge into a point, all right, or diverge from a point. So we can't determine the angle between these two vectors. Therefore, we have to produce a line, mean we have to extend one of the line. Both can be extended, up to you which one you want to choose. Let's say I extend E, okay, make E longer. Now you see, this is E also, right? It's still E, right? It just go longer only. It's still vector E. So you see now the two vectors E and F, okay, diverge from a point. So the angle between these two vectors will be here, and not this one. All right. So I show you some more examples. Okay, so let's say, what's this? Let's say if we have two lines like this, see? So the angle between these two vectors can be this one, which is converge into a point, or this one, which is diverge from a point where they are the same. All right, so if you have one situation like this, you see, one in but one out. So we have to extend one of it. So let's say I extend this one. When I extend this one, you see that from here to here, these two vectors diverge from a point. So the angle between these two vectors will be this one. Okay? Or you can make this one, I can make the arrow here. Same, right? It's still same direction. So I can take this angle also. This is also the angle between the two vectors, where they are the same, right? Okay. And the angle between two vectors will be 0 to 180 lah. It can be acute, it can be obtuse. Obtuse. It can be acute, it can be obtuse. All right. Okay, so next. All right, the scalar product. So now when we know how to define the angle between two vectors, then now we can do the scalar product, right? Because it involves the anchor between the two vectors. All right, so what is scalar product, right? Or also known as dot product or inner product. Some books they use dot product, some books they use inner product. Why dot product? Because they're using dot, you see, a dot. All right, so the scalar product of two vectors, vector A and B, is defined as, this is how we calculate the scalar product of two vectors. So A dot B, you see dot lah. The formula is modulus A multiplied modulus B cos theta. Or we just read as A dot B. Okay? With theta is the angle between vector A and B lah. So you know how to define the angle between two vectors already, right? From here. Okay? So from here you can see that A dot B is actually become a scalar, a number, no more vector. And not a vector. A dot B is not a vector. This product, the answer, is not a vector, but is a scalar, means a number. Because modulus A is a number, modulus B is a number, cos theta also a number, right? This is why we call it scalar product. All right? So remember, A dot B become a scalar. It's not a new vector. Not like last time when we learned A plus B. Vector A plus vector B, this is a new vector, right? Or vector A minus vector B is a new vector, okay? Or vector multiplied to a scalar K is still a new vector. But scalar product, A dot B, is not a vector, it's a number, a scalar. Hence, A dot B dot C is not defined. All right, so remember, for this scalar product, dot must be vector dot vector, then get a number. All right, it must be vector dot vector. So this is not defined. Why? Because A dot B is a scalar. A dot B is a number. So a number cannot dot to a vector. All right, for scalar product dot, it must be vector dot vector. Therefore, this is not defined. But A dot B multiplied C, yes, it can be. Is it no more dot, just multiply? So this one is defined because A dot B is a scalar. Let's say lambda lah. All right, then lambda can be multiplied to a vector, right? So you see how important the dot is. With the dot, no, it's undefined. It's wrong. Without the dot, yes, can. All right, so be very careful with this concept. Okay. Okay, so by using this scalar product, definitely why we learn scalar product, definitely you can use it to find something, right? Okay, the first one that we can use the scalar product to find out is parallel vectors. All right, we can use scalar product to define parallel vectors. Okay, how to define parallel vectors? All right, okay, so A, if two vectors A and B are parallel and in the same direction, then theta will be 0. The angle between them 0 because they are parallel and same direction. All right, so if theta is 0, cos 0 is 1. Cos 0 is 1. Therefore, A dot B become modulus A modulus B. All right, so the condition is like this. Okay. So just now number 2, we already know if you have two vector cross like this, then the angle between them is theta. Then A dot B will be modulus A modulus B cos theta. All right, so if two vectors are parallel and same direction, so this is the diagram. Let's say vector A is the black color one to this direction, and B is also another vector, but parallel and same direction as A, like this. All right, parallel and same direction. So the angle between them is 0. There's no angle between them. All right, therefore cos 0 is 1. Therefore, A dot B become modulus A modulus B only. All right, so this is the property of two parallel vectors with same direction. Okay, so next. All right, next. B, if the two vectors A and B are parallel but in opposite direction. Opposite direction, then theta will be 180. Later I show a diagram how it become 180. And cos 180 is -1. So hence A dot B become negative modulus A modulus B. All right, so it is like this. Okay, you see, this is the meaning of opposite sign. So let's say vector A from this point, vector A is to the left and vector B is to the right. You see, opposite direction, parallel but opposite direction. Therefore, the angle between so this is the point where the two vectors diverge, right? So the angle between this one will be theta. So theta is 180. Okay. So as conclusion, if two vectors are parallel and same direction, then A dot B become modulus A modulus B. If they are opposite direction, parallel and opposite direction, then A dot B will become negative modulus A modulus B. Okay? And one more thing that I want to explain is this one. This is the formula for a scalar product A dot B. So from this formula, we actually can calculate the angle between, right here, the angle between two vectors. You just rearrange this one. All right, we just rearrange. So means that we keep cos theta here. We shift modulus A modulus B to the left hand side. Therefore, cos theta is A dot B over modulus A modulus B. So we can use this formula, all right, to calculate the angle between two vectors. Okay, all right, so this is the first advantage of this formula, the scalar product. We can use the scalar product to define two vectors which are parallel in same direction or opposite direction. All right, okay, so the next one, the next important one for this scalar product will be, we can determine whether two vectors are perpendicular or not. All right, to determine perpendicular vectors, or in some books you see they use the terms orthogonal. Orthogonal vectors means perpendicular. Okay, how we determine? By using scalar product, how we can determine two vectors are perpendicular to each other. Okay, A, if two non-zero vectors A and B are perpendicular to each other, so perpendicular means theta equals 90. All right, so cos 90 is 0. Yes, therefore A dot B will become 0. This is a very important statement. All right, so when you get A dot B and you get 0, means that these two vectors A and B are perpendicular to each other. All right, normally in this case we will use the IJK formula to calculate. Okay, if A is perpendicular to B and given that vector A is xy and vector B will be k negative yx, all right, where k is a scalar. So this means that in two dimensions there is an unique perpendicular vector to the given vector. So this is for two dimensions. So in two dimensions, if vector A is xy, then vector B will be negative yx. All right, only one negative yx. So A and B, when you multiply, they will be equal to 0. Okay, so in two dimensions, there is only one perpendicular vector to the given, let me see, to the given vector. Also in two dimensions, so each vector only have one perpendicular line. Okay, in two dimensions. But in three-dimensional, there will be more than one vector from different direction, but they are perpendicular to a given vector. All right. So we'll this one, if we use the object to explain, very simple. Let's say imagine this is a vector. Okay, this is a vector. Okay, this is a vector in three-dimensional. So this one is a vector perpendicular to this one, right? 90 degree. But this one also, right? If a vector like this intersect with the red color vector, it is also perpendicular, right? Let's say I turn. So you see? So I just turn back. It's still perpendicular, right? So there are many vectors can be perpendicular to this vector from different direction. Can be like this, can be like this, can be like this. Okay? As long as it's perpendicular. So this is the meaning. In three-dimensional, there are many vector that can be perpendicular to a vector. All right, not like two dimension. Two dimension, each vector only have one perpendicular vector from one direction now. Of course, it can be like this, like this, same direction, right? The only vector, maybe you will see that there are many vectors that perpendicular, but they are all same direction, right? But this one is from different direction, but they are yet perpendicular. Okay, so there will be one example in your textbook, page 260. So you can open your textbook. Okay, my one is 260 lah. There's an example to prove it. Okay, there's one example to prove it. To prove by using the calculation of A dot B lah. Okay, so from here we actually we are going to learn how to do A dot B by using the XYZ component. All right, but before this we have to learn a little bit also lah, because it's very simple. Okay, so let's say this is how they prove. All right, let's say you are given three vector. Vector A is like this, vector B is this one, vector C is this one. So you see they are all different from different direction. Okay, so this one is A dot B. A dot B dot. So actually A dot B by using XYZ, very simple. The calculation very simple. All right, X multiply X. So 2 times 1, 2. Plus Y multiply Y. So -1 times 5, -5. Then become -5 lah. Or actually it's plus -5. And plus X, Z plus Z times 3 times 1, 3. Very simple, right? Just X times X component multiply X component, Y component multiply Y component, Z component multiply Z component. All right, then you add up all the answer, equals 0. See, A dot B equals 0, means A and B perpendicular to each other. This is A dot C. Now this is A, this is C. All right, so X times X, 2 times 3, 6. -1 times -6 plus 6. 3 times -4, -12. 6 plus 6 minus 12, 0 also. So A dot C is 0. So means A perpendicular to C. So you see, in 3 dimension, A perpendicular to B. A can be perpendicular to C also. All right? But in 2 dimension, there will be only one. Okay? Okay. So this is how we use scalar product to determine 2 vectors are perpendicular. So later you will see many past year questions ask about perpendicular vectors. Okay, then D, the 0 vector is perpendicular to every vector. You know 0 vector, right? No direction, no magnitude, just a dot. So it is perpendicular to every vector. All right, so here number 9 will be some properties of the scalar product. Okay, the first one, scalar product is commutative. All right, commutative means A dot B same as B dot A. Okay, why the same? Okay, this is how we prove it. Okay, A dot B is modulus A modulus B cos theta. This is number, this is number. So we know that multiplied 2 numbers are commutative, right? So I can write as modulus B multiplied modulus A. Okay, A dot B is modulus A modulus B cos theta. So modulus B modulus A cos theta will be B dot A. Okay, so A dot B and B dot A are commutative. Remember this property. They are commutative. A dot B same as B dot A. Okay, number 2. If we multiply a lambda to the scalar product, it will be the same. You can put the lambda wherever you want. You see, I can multiply lambda to A, then only dot B. I can multiply lambda to A dot B, or I multiply lambda to B, then only A dot lambda B. They are all the same. All right. So this is commutative, one part of the commutative also lah. This is commutative vector dot vector. This is commutative how to say that, scalar multiplied with a vector. All right, so second property will be scalar product is distributive. Distributive means like this, A dot B plus C. Remember, B plus C is a new vector, so it can be like A vector dot vector. So it can become A dot B plus A dot C. Okay. So this distributive. All right. So there's one example in page 261. Example 6.6261. Open your textbook. Page 261. All right. Example 6.6. This one. I'm not going to go through this one. This is a step how they prove it. How they prove this distributive. How they prove that scalar product is distributive. Okay. This is how they prove it. Okay. You can go through yourself. All right. I'm not going through this because it's quite simple. I think you can understand. All right. And third one, scalar product is non-associative. Non-associative. All right. Means A dot B dot C not same as A dot B dot C. And also cannot lah. Just now remember number 6. Number 6 that we are talking just now. Here. Okay. It's not defined. Because A dot B is a number. A number cannot dot a vector. Dot only for vector, dot vector. Alright, so this is non-associative. Okay? Alright, so now we will see. Okay. Alright. So now we will see non-associative, what just now we're talking about. Okay, so now we will see proof that the diagonals of a rhombus are perpendicular. Okay? Alright, so just now we talked about this already. Perpendicular letter, theta 90, so cos 90 is 0. So you get 0. Now we are going to prove that the rhombus, we know that the diagonals of the rhombus bisect each other. Rhombus, rhombus means parallelogram. It's a parallelogram, but 4 sides all equal. Okay, equal length. And we know that all the rectangle, square, parallelogram, rhombus, okay, they are diagonal bisect each other. But for rhombus, there is a special characteristic for the diagonal. They are not just bisect each other, but they are perpendicular. Okay, so this question wants us to show that the diagonals are perpendicular. Okay, so we draw a rhombus, and let's say we name it as A, B, C, D like this. Okay, so let's say AB is, I represent by vector A lah. Later easier to calculate. Okay, BC is B, DC is also A lah, because it's parallelogram. AB is A, DC also A lah. AD also B lah. BC is B, AD also B. Alright. So we want to check the diagonals, right? So diagonal is AC and BD. Okay, AC is AB plus BC, right? AC is AB plus BC. So means A plus B lah. Okay, whereas BD, I go this direction lah. BD is BC, CD. So BC is B, CD is nearly A, right? DC is A mah, so CD is nearly A lah. Okay, so we check their scalar product. Okay, we check their scalar product, whether it's 0 or not. If 0 means they are perpendicular. So AC dot BD. So AC is this one. BD is this one. Okay, AC dot BD. So by using the distributive law, remember, scalar product are distributive, so we can expand them. So we can expand them. A dot B minus A dot A, B dot B minus B dot A. Okay, distributive law. Alright, then just now we already know, right? Scalar product are commutative. BA and AB same. Okay, B dot A can write as A dot B, right? So A dot B minus A dot B, no more lah. Okay. This is the concept that we haven't go through yet. It's actually here. Doesn't matter. We can show here. We can prove here also. All right. Another one is this one. Okay. So A dot A means A dot A. So means A and A parallel and same direction, right? A and A are two vectors which are parallel and same direction, right? So A dot A will be modulus A modulus A. Okay. A dot A parallel same direction. So theta equals 0. So when two vectors are parallel and same direction, then A dot A will become modulus A modulus A. So modulus A means modulus A square lah. Okay. Negative is here, so A dot A is modulus A square. So B dot B is modulus B square. Alright, and because this is rhombus as I said just now, rhombus, all the four sides are equal. No, their modulus are equal. Okay, so modulus A and B are the same. Therefore, if these two are the same, so negative plus positive, no more, 0. Yes, so we already get that AC dot BD equals 0. Therefore, the conclusion will be AC perpendicular to BD. So AC perpendicular to BD. Their diagonals, the diagonals of a rhombus are perpendicular to each other. Okay. All right, so this is the concept of perpendicular of two vectors. Okay, next, there is one more concept that is a little bit complicated, but so far we seldom use. Also, you try to understand it. Okay, so it says that this concept is perpendicular projection. All right, so later we will see the diagram. What is perpendicular projection of one vector onto another vector? All right, so we will see some example in your textbook. Okay, page 258 to 259. All right, open your textbook, page 258. Yeah, here. Okay. This one, perpendicular projection. Okay, so what is perpendicular projection? So the concept is like this. Let's say I have two vectors. So let's say now I'm talking about an important use of scalar product is in the determination of the perpendicular projection of a vector B onto A. All right, so the concept is like this. Let's say I have two vectors. You see, this is vector A. This red one is vector A along here. Then this is vector B. Okay, so both vectors diverge from a point. So this theta will be the angle between A and B. Okay, so now you imagine that, there is one lights here, lampu. Alright, there is one lights here. So this is a stick. If you have a lights on top the stick, so you have shadow, right? Correct? Of course, you will see shadow on the plane. Yes. So from this, let's say vector B is from O to B. So from B, you draw a perpendicular line to vector A. Okay? From B, you draw a perpendicular line to vector A. Let's say this perpendicular line drop on point P. Okay? So OB will be point P. Point P is the perpendicular projection of vector B onto vector A. See that? So this is the example. This is the meaning of perpendicular projection. So if theta is acute, then the perpendicular projection is like this. How about if the angle between A and B are more obtuse? Okay, so now you see. This is vector A. The red color is vector A to this direction. And now B is to this direction. So this is the angle between A and B. Alright, so how to draw the perpendicular projection? So we have to extend line A, vector A, to the left hand side. Then again, let's say B is from O to B. So from B, we draw a perpendicular line. So this is point P. Therefore, now the perpendicular projection will be OP in this direction. It's still B onto vector A. Alright, so if the angle is acute, then the perpendicular projection P will be same direction as A. If the angle is bigger than 90, then the perpendicular projection will be opposite direction of A because onto A. Alright? Okay. So this is B onto A. Alright. How to calculate this P, vector P? So the vector projection of P onto A is a vector P that lies on the line contained A. So if theta is acute, P has the same direction of A. If P obtuse, P is in the opposite direction of A. Just now I have explained in the diagram, right? Okay. So OP is modulus B cos theta lah, correct lah? We go back to this direction. Or let's say we use this one lah. Okay, let's say we use this one lah. Okay, easier. So you see this is a right angle triangle. Alright, this is cos theta. So OP is here. So OP is adjacent. Modulus B is hypotenuse. Alright, so OP over modulus of B, adjacent, hypotenuse, cos theta. Alright, therefore, move your modulus cos theta to this side. So OP equals modulus B cos theta. This is how this come from. Okay, and just now remember we have said here. Okay, just now we say scalar product A dot B is modulus A modulus B cos theta, and cos theta is shift the modulus A modulus B to this side. So we sub in cos theta equals this thing. Okay, we sub in here. Okay, then modulus B can be simplified. So therefore, OP is A dot B over modulus A. Alright? And what is this? A over modulus A is the unit vector, right? Unit vector in the direction of A. Alright? So this is how we calculate the perpendicular projection. Alright, so the length of OP is the perpendicular projection of B in the direction of A. You can just imagine that it is the shadow of line vector B, or the shadow drop on vector A. Okay, so just now is B onto A. Okay, how about A onto B? Okay, A onto B. Yeah, this one. A onto B. Okay, this is B onto A. Alright, B drop onto A. So how about A drop onto B? So if A drop onto B, so imagine now B is the horizontal plane, like, okay? So this is A. So we want A drop on B. So the light will be here. So the shadow of vector A drop here. See? This is still P. So this is vector P. Okay? So this is A onto B. Alright? So A dot B same with this. Then B cos theta like just now is OP. Okay? It's actually this thing come from here. Because just now this one equals to OP already this one. Yeah. So if B onto A, so A dot B will be modulus A OP. Alright? If B drop on A, then it's another way around. Okay? So this is the concept of perpendicular projection. Alright? So in the textbook, it show very clear. Okay. So I repeat again. So I hope you understand. Alright? So this one is for anchor is acute. So B onto A. So this is A. So this is B. So from B, we draw a perpendicular line. And mark this one as point P. So this is the perpendicular projection, OP. Okay? If theta is more than 90, obtuse anchor. Alright? Then we have to extend the line for A. Which one to extend? It depends what onto what lah. So now I'm B onto A so I have to extend A. If A onto B, then we extend B lah. Okay? Then say from B, we draw a perpendicular line. So mark this point as P. So OP will be the perpendicular projection. Alright? So by using the this one, cos theta. So cos theta is OP over OB. All right, therefore shift this one here. OP is OB cos theta. All right, this one just I have explained. OB is modulus B. Cos theta, we sub this formula. Simplify. All right, after simplify, then you get this. Sorry. Okay, like this. And get into this one. So this is B onto A. All right, where else? A onto B. A onto B. Let's say the same line, right? A onto B. So now A drop on B. So you are going to, from A, draw a perpendicular line to vector B. Then this is your P. Okay, so by using the same concept, you can find the formula to calculate the length of the line OP. All right. Okay. Okay, so this part is all about concept, right? We have no question yet. When involve calculation, we actually involve IJK. All right. Okay, say scalar product in Cartesian form. So the scalar product of two vectors A and B, which is A dot B, is valid whether both A and B are two-dimensional vectors or both are three-dimensional vectors. So means that this scalar product is for 2 dimensions and 3 dimensions also. Okay, these are some basic calculation in Cartesian form. All right, so if theta is 0, remember what is theta 0? Parallel, same direction. So A dot B become modulus A modulus B, right? Just now we have shown this one. So A dot A and A definitely are parallel and same direction, right? So will be modulus A, so become modulus A square. Remember just now we used this concept? Okay. So B dot B also same, become modulus B square. In that case, I dot I also we know, I the unit vector in the position of in the direction of x-axis. So it's I modulus I. Modulus I is unit vector so one unit only. So I dot I is 1. J dot J also 1. Okay, K dot K also 1 now, of course. If perpendicular, A dot B 0, right? So we know I and J perpendicular. So I dot J 0. J dot I also 0. This 2 dimension. This 2 dimension. So if 3 dimension same lah. I dot J, I dot K also 0. J dot K also 0. There I, J, K, these 3 are perpendicular to each other. Alright? So not only I dot J 0, I dot K, J dot K all 0 because they are all perpendicular to each other. Okay, now we see the calculation. As I said just now, very simple. Let's say I have 2 vectors R1 and R2 in IJ form. Alright, therefore R1 dot R2 will be like this in Cartesian form. So just multiply the x component. X1 multiply x2. See? And then I dot I. Alright? Then x1 multiply y2. Alright? Then you have I dot j. x1 multiply y2 and I multiply j. I dot j lah. Then y1 x2 j dot I. This one. And this one y1 y2 j dot j. Okay? So remember what we have discussed here? We are going to apply. So I dot I is 1. I dot j 0. J dot I 0 because perpendicular This one parallel 1. J dot j also 1 parallel. Therefore the answer left x1 x2 plus y1 y2. It seems like just as I said just now, just multiply the x component plus multiply the y component. Okay, this is in the simpler way. If you write in vector column form, then it will be very simple. Okay, so the actual what happened is like this lah. The actual what happened is like this lah. Okay, so if we write in vector column form, very simple. X multiply x plus y multiply y. This for 2 dimension. And just now we also showed Okay, cos theta is this one. From the scalar product formula, we can calculate the angle between the two vectors. So cos theta is this one. So R1 dot R2, this is a formula. Modulus R1 is Z, x squared plus y squared, right? X squared plus y squared. Okay, so we are going to use quite often this formula. Okay, this is for second two dimension. So number 5 will be 3 dimension, same. Same thing, just that add one more Z component. So when add one more Z component, when we expand, then you have x1 Z2 I dot k, this one. x1 Z2 I dot k. Or just add this one. This first two just now 2 dimension have already. This one also. Okay, and this one. All right, so as usual, I dot k is 0 because perpendicular. J dot k also 0. K dot k is 1. K dot j, k dot I, all these are 0 because they are perpendicular. I dot j, j dot I also 0. So all this disappeared. So left, I dot I is 1. All right, then left, y dot y. Sorry, j dot j, 1. So y1, y2. Okay, and the third one, k dot k is 1. So z1, z2. All right. Therefore, from this formula, from the result from this one, we can apply into the column vector form. So immediately we know this is the answer. You see x multiply x, y multiply y, z multiply z, and just add them up. All right. And this is the formula. Okay, to find the cos theta. All right. So this is the scalar product in Cartesian form. Okay, so we will have a lot of examples from here. Okay, so example 6.1.3.5. Okay, so first we are going to see the questions in checkpoint 6.2 or page 262. So please prepare your textbook. All right, checkpoint 6.2. My one is page 262. All right, so I do not know whether your textbook same with me or not, so I let you snap the question first, then later you can check. All right, so it is question 1 to question 10. Okay, then I push up a bit. Yeah, 11 and 12. Okay, the question that I take will be the question that I'm going to discuss. All right, I'm going to discuss 1B, 2C, 4, 7, 10, 11, 12. All right, then others than that, you are going to do it as your homework. All right, I can 5, no problem, you will know perpendicular concept. 6, you can draw this diagram, you see, A, B, C. You use this diagram, then you use the concept CB dot CA. After you expand, you should get 0. All right, then you know that it is right angle. I just explained to you lah. 8 also, you can use this diagram. All right, so remember the area of triangle ABC. Last time in Form 5 you have learned. A, B, sine theta. Okay, so others should be no problem, not difficult. All right, so so this question 2 will be homework. Later I'm not going to show this page anymore. Okay, let's start exercise 6.2. Okay, I don't know how to show together. Can Okay. Question 1. Find the scalar product of the following vectors. This is a simple one. So you are given 2 vectors. Find their scalar product. All right. I prefer use vector column lah. Easier. Column vector. Sorry, I use column vector easier. If you want to use the IJK form, also can. Or up to you. Okay, so you are given. Let's say we name it vector A and vector B lah. Or easier ma. So we want to calculate A dot B. So this is A dot B. So please don't skip this step lah. Show. Okay. Then multiply lah. this one times this one negative 6, this one times this one negative 2, this one times this one 12, answer is 4. So you see, you will get one integer, not integer, sorry, you will get one number. Okay, so it become a scalar. That's why we call it scalar product. All right, then question 2C. Find the cosine of the angle between the following vectors. Okay. All right, find the cosine of the angle between the following vectors. So you are given two vectors A and B. All right, A is 6i minus 8k. No j, right? No j means 0 lah. So you are given two vectors. Find the cosine of the angle. They don't ask you to find the angle. They ask you to find the cosine of the angle. All right. So this is the question. This is the answer. So you are given vector A and B. Remember just now we say 6i minus 8k. No j. So means that the j component is 0. So from this formula, okay, the scalar product, excuse me, formula, so we can get cos theta. So this question, they would just want us to find cos theta only. So first, we need A dot B. So I calculate separately lah. A dot B. So 6 times 2, 12. This one 0. This one positive 48. So 60. Alright, then we need modulus A. Still remember how to find the modulus of A. So you get 10. And modulus B. This one. So you get 7. Alright, then sub all this value into the formula. So A dot B is 60, modulus A is 10, modulus B is 7. So 6 over 7. So the question just want you to find the cosine of the angle. So actually can stop here for this question. But if you want to go further to calculate the angle, then will be you press the calculator, shift cos this one, then you get is 31.0 degree. Remember, all the answer in degree must have one decimal place. Remember this. Okay, all right. Then next we will go to question 4. All right, question 4. The position vector of points P, Q, and R is given. You see, you are given 3 vectors here. You see the excuse me. The second one is JK, 1J, 1K. So no I. No I means the X component is 0. All right. So you are given. So you see, I name it the position vector of PQR. So OP, OQ, and OR. So I write it in column vector form. Okay. Number 1, find OP, QP dot QR. Then find anchor PQR. All right. So this is question 4. Okay, first part, QP dot QR. Okay, QP dot QR means I need QP. So QP is QP OP minus OQ dot QR is OR minus OQ. Remember the position vector formula. So I directly do lah. So this is OP minus OQ. This is QP lah. Dot. This is OROQ, so this is QR. All right, so this is minus only. So minus, you get this thing. This one also minus, you get this. Now you do scalar product. So negative 18 minus 32 minus 8. So the answer is negative 58. Okay. So part B, you're asking to find angle PQR. So I sketch the triangle PQR. PQR. Okay, angle PQR means this one. The question 1, this angle. So we know that by using scalar product, to get this angle, you must have QP and QR. Here, you see, this is why they ask you to calculate QP, QR first. All right, now QP dot QR, the formula is modulus cos theta. So QP, QR is negative 58, right? Just now calculate already. Modulus for QP, modulus for QR, cos theta. All right, so cos theta will be negative 58. This is square root 29. This is square root 116. So shift it here. And if you use a calculator, you get that the answer is negative 1. Cos theta equals negative 1. So means theta is 180. All right. Cos theta negative 1. So you remember this cos graph, the graph of cosine. Negative 1, only 1 point here. And this is the center, so 180. So what is the meaning? the question tell you this angle is 180. What does this mean? Can you think of it? What is the meaning? This angle is 180. Yes, I hope you understand, huh? This, if the PQR is 180, means it is collinear. PQR. So angle PQR 180. Yes, it's actually show you that PQR are actually collinear. So see or not, by using this formula, scalar product concept, yet we can prove 3 points are collinear, right? Okay, question 7. Okay, next one will be question 7 here. You are given vector A and B are non-zero, okay? And also given modulus for A plus B same as modulus of A minus B. This is given, show that A and B are perpendicular. Okay, so you're only given this and you're asking to show A and B are perpendicular. So by using scalar product to show two vectors are perpendicular, so A dot B must be equals 0. This is our direction. All right, A dot B, I must get A dot B equals 0. Then I can make conclusion A perpendicular to B. Okay, how to get A dot B equals 0? There is only one information given to us. This one. All right, modulus for A plus B same as modulus for A minus B. All right, so the next step is actually I'm going to square both sides. Can, right? I'm going to squaring both sides. All right, so square both sides means modulus A plus B dot modulus A plus B. Remember this concept? Where is it? Okay, here. Remember this concept? If you square a modulus, you square the modulus of a vector, it's actually same as the vector dot itself. See? We are using this concept. Okay? So the square of the modulus A plus B, so means A plus B dot A plus B. So right hand side also the same. Square of the modulus A minus B is A minus B dot A minus B. Okay? The notes page 13 is just now what I shown. And again, we are using the distributive law. Distributive law. So A dot A plus A dot B plus B dot A plus B dot B equal. I don't have enough space, so I write at the second column. So A dot A minus A dot B, okay, minus B dot A plus B dot B. Okay? So you see A dot A and A dot A can be simplified because one is at the left hand side, one is at the right hand side, so can be simplified, minus out. B dot B and B dot B also can be minus out. Okay, so left hand side, this is left hand side. Okay, and we know that A dot B and B dot A same, or actually these two are the same. So 1 plus 1, 2 lah. So I have 2 A dot B. Here also B dot A same as A dot B, right? So minus A dot B minus A dot B same as minus 2 A dot B. Okay, so shift this one here, plus 2. So become 4 A dot B. Alright, equals 0 already. So 4 shift here, so A dot B equals 0. This is what I want. That's why when you are asking to prove that two vectors are perpendicular, so your direction is, you must find this one. Their scalar product equals 0. Okay, use the information given to you, try to get the scalar product equals 0. Then you can make conclusion A and B are perpendicular to each other. Alright? Okay, next is question 10. Alright, so 8 and 9 you can do yourself. It's similar question. Okay, I give you the hints already. 8 and 9 do yourself. Okay, we are going to see 10. So question 10 say, again, you are given two precision vector of point A and point B relative to AO will be A and B, such that modulus A and modulus B same. Okay, this is the information given to us. Modulus A same as modulus B. Show that the vector A plus B is perpendicular to the line AB. Alright, so show that these two vector A plus B and AB, they are perpendicular to each other. So it's similarly to question 7, right? So if I want to show that this one and this one perpendicular, so I must find their scalar product. Scalar product for A plus B and AB. Alright, and I should get the answer 0. So it's quite similarly to question 7. Alright, just slightly different only lah. Okay, so this is given modulus A and modulus B same. Alright, and just now we say we want A plus B and AB, right? So what is AB? AB is OB minus OA. OB is B lah, OA is A. So AB is B minus A. Alright, so I want to show that A plus B and AB are perpendicular. So I must find their scalar product. This one suppose is A plus B dot vector AB lah. Okay, and from here we show already vector AB is B minus A. Alright, then by using the distributive law, same again, A dot B minus A dot A plus B dot B minus B dot A. Okay, so A dot A is modulus A square law. Remember, B dot B is modulus B square law. This one cannot. A dot B, you don't write modulus A, modulus B, you know. Okay, it's different. So because just now here given my modulus A and modulus B same, so negative plus positive, no more. This one's 0. So left, A dot B minus A dot B. A dot B. B dot A also A dot B, right? Commutative ma. B dot A same as A dot B. So this one 0. A dot B minus A dot B also 0. Okay? Therefore, we find that the scalar product between these two vectors equals 0. Therefore, we can make conclusion, this vector perpendicular to this vector, and this is actually your AB. Sure no? So now from here you see how we can use scalar product. Alright? Okay, next. Question 11. Okay, so question 11 say A and B are 2 points which have the position vector. So you are given OA, OB. The point P lies on AB such that AB to the ratio of AP to PB is lambda 1 minus lambda. Okay, so the diagram will be something like this. AB, so P lie on it such that the ratio is lambda 1 minus lambda. Okay, so this is the information given to us. So you are asking to find the position vector of P. The value of lambda is OP is perpendicular to AB, and the shorter distance from O to AB. All right, this is question 11. Okay, so we start. All right, remember this formula? The last video we have discussed. Okay, so you are given vector OA, vector OB. The diagram is like this, and P divide AB follow this ratio, right? So we can, this is a formula to find the position vector of OP. Lambda multiplied with this vector, 1 minus lambda multiplied with this vector. Then lambda plus mu. Okay? Therefore, OP is lambda, OB, 1 minus lambda, OA. So lambda plus 1 minus lambda. Okay, so you see this one, lambda minus lambda no more. So the denominator left 1, so can forget about it. Alright? Yeah. Then, you see, minus 2 lambda. I straight away right here, minus 2 lambda. This one, 1 minus lambda times 4 is 4 minus 4 lambda. This one 4 lambda. 1 minus lambda times 1, 1 minus lambda. This one 1 lambda. 1 minus lambda multiplied negative 2, so negative 2 plus 2 lambda. Okay, then I simplify because the question wants us to find the position vector of OP, and they give us the information in IJK form. Okay, so the final answer also in IJK form lah. Remember this concept. All right. So this one after simplify is 4 minus 6 lambda I. This one 3 lambda. So 3 lambda plus 1 J. Okay, this one 3 lambda minus 2 K. All right. Okay, so B, they say if OP is perpendicular to AB, find lambda. All right. If OP is perpendicular to AB, find lambda. So OP we have already from here. We have OP already. So I need AB. So I calculate AB first. So AB is OB minus OA, OB minus OA. So this is your AB. Since OP perpendicular OB, so the scalar product equals to 0. Okay? So this is OP. Just now simplify already. This is AB. Equals to 0. Then multiply. X multiply X component. So negative 6 times 4, negative 24. Positive 36 lambda. Okay? So this one also the same. 9 lambda plus 3. This one 9 lambda minus 6. Okay? So altogether you have 54 lambda. This one negative 26. Negative 27. Shift it to the right. So become like this. Therefore your lambda equals half. So if OP perpendicular to AB, lambda will be equals half. Okay? Okay, C, shortest distance. So in chapter 5, you have learned the concept of shortest distance, right? Yeah, shortest distance is the perpendicular distance. Alright, so let's say this is AB. So the question says shortest distance from O to AB. Alright, so as you have learned in chapter 5, the distance from O to AB can be a lot can be. But the shortest one definitely is the perpendicular distance. Remember this concept, huh? So the shortest distance from O to AB same as OP lah, because just now we already confirmed OP and AB perpendicular to each other. Therefore, the shortest distance from O to AB will be the modulus for vector OP. Alright, the modulus for vector OP. So just now, this is OP, right? Okay, this is OP. And lambda is half. Just now we calculate already. So just sub in. When lambda is half, so OP is, half is 3. 4 minus 3, 1. So 1i. Okay, when this is half, so 3 over 2 plus 1, 5 over 2. So 5 over 2j. So when lambda is half, so 3 over 2 minus 2, negative 1 over 2k. When lambda equals half, this is your OP. So find the modulus, sub in all the component. Okay, so after simplify, is half multiplied square root 30. Alright, question 11 looks like very long, right? But actually, yeah, just apply formula only. Formula for this. Okay, perpendicular concept. Shorter distance concept, also related to perpendicular. Alright, okay, next. Question 12 of 6.2. Alright, question 12 for 6.2. Here. Alright, so refer to the origin OA and B are 2 points which have position vector A and B respectively. Okay, prove that P, whose position given. So you are given the position vector of point P already. Here, lambda A plus 1 minus lambda B. Alright, prove that they are collinear with A and B. Collinear. Alright, so this is first part. Second part, given that vector A, vector B is like this. Find the angle between OA and OB. Then find the two possible value of lambda for which angle AB and OP is 60. Okay, two different parts. So you cannot apply this A and B into this one, This is separate. Okay, so let's see how to answer this. Okay, so this is question 12. So this is line AB, P lies on it. And you're given that OP, I use small letter P lah, is lambda A plus 1 minus lambda B. A is OA, B is OB. Yeah? So first I have to calculate AP first, because they want us to show that it is collinear. They want to show APB collinear. So remember the concept for collinear. From APB, we must form at least two vectors. You can form AP, AB, PB, up to you. So for me, I'm going to use AP and AB. Right? So I find AP. AP is OP minus OA. So this is OP law given. This is OP minus OA. Alright, so expand it. Lambda A minus A. So lambda minus 1A lah. I see this is 1 minus lambda. This is lambda minus 1. I want to make them the same. So this one, I factorize out the negative 1. Okay, become negative 1 minus lambda A. So 1 minus lambda, 1 minus lambda, I factorize out. So it become B minus A. Okay, so I get my AP. Alright, then I calculate my AB. So AB very simple, OB minus OA. So B minus A only. So from here you see AP is 1 minus lambda, B minus A. And B minus A is AB. Alright, so from here I can make conclusion. AP is 1 minus lambda AB. Okay, so remember when we can find the relation between two vectors, our conclusion is AP parallel to AB. And I see one common point A. Parallel and common point A. Therefore, A, P, and B are collinear. Okay, so this is the first part to show A, P, and B are collinear. Okay, second part, you are given vector A is I plus J. So no K. So this one is 0 lor. Vector B is 4, negative 2, 6. Like this. Okay, the question wants you to find the angle between OA and OB. So use the formula, cos theta equals A dot B modulus A modulus B. This is A dot B. This is modulus A. This is modulus B. Just calculate. So you get 2 over square root 112. So press your calculator. Theta is 79 degrees 6 minutes. You can write your answer in degree and minute. Or the calculator can help you to change. Or if you want to use decimal, then remember 1 decimal. Okay? So this is the second part. And the last part is find lambda if the angle between OA and OP is 60. Alright? Now, OA, OP, the angle is 60. Find lambda. Okay, since we have angle between OA, OP, so A dot P lah. Modulus A, modulus P, cos 60 lah. This is A dot P. A and P. Alright, I don't have enough space. Okay. I actually show you how to find P here. Just now the question say, right, this is P. So lambda A plus 1 minus lambda B. Okay, so lambda, this is A, 1 minus lambda B. So combine everything, you get this. Alright, this is your vector P. So A dot P equal to, this is square root A, this is square root P, and also square root. Square root modulus P. Alright, and cos 60 is half. I don't have enough space, therefore I split it into 2 lines. Okay, left hand side, just multiply. Okay, you get this, left hand side. Right hand side, square root 2 over 2. Then I expand. I expand all this square. I expand all this square. You get all these terms. You get all these terms. Just expand. Alright, you can check later, one by one. Okay, here, square root 2 over 2, I shift it to this side. Because 3 lambda minus plus 3 lambda no more. 4 minus 2 is 2. So 2 shift here, become 4 lah. This one left 2 only, right? So shift 2 here, multiply, so 4 lah. Square root 2, go down here. Okay, so inside the square root, after I simplify, become 54 lambda square minus 108 lambda plus 56. Then the next step is I square both sides. All right, so square both sides. This is 16, this is 2, so 16 over 2, 8. This one very simple, square root square no more. Okay, so after simplified, so this one shift here 48. So this is a quadratic. You get one quadratic equation. All right, simplified by 6. I simplified by 6 first, then factorize. Therefore, your lambda is 2 over 3 or 4 over 3. Okay, so this is question 12. All right, so I discussed quite many questions in chapter point 6.2. So others, suppose no problem for you to solve it. Okay, you must try, you must try, then you will see it. Okay, so now we go back to our notes. Okay, go back to our notes. Where is it? Okay, here. Okay, go back to our notes. Okay, so just now I have discussed question 1, check point 6.2. Okay, this question 2 you do as homework. Find the scalar lambda so that this vector is perpendicular to the sum of this vector. So means sum. So means you add these two first to get the new vector. Then find the scalar product lah. Or perpendicular equals 0. So from there you find the lambda. Okay? Okay, next page will be, you see. It's actually this part, you see, came out in STPM quite often. 2002, 2006, 2007, and 2011. It came out 1, 2, 3, 4, 5 times. All right. See the red color one, So after finish this video, question 3, 4, and 7 will be your quiz. No problem. I think you can do. After we have discussed so many questions, definitely you can do. All right. So right after you finish the video, please complete your question 3, 4, and 7 as a quiz. All right. So I'm going to discuss another 2, question 5 and 6. All right. So question 5, STPM 2007. Okay, the position vector of the point A, B, C, D relative to an origin is given. This is a 2-dimension question. Okay, part A, show that for any value of x for which A, B, C, D is a parallelogram. This question we have discussed. All right, you can check. Let me see. 6, 7. Okay, here. Okay. Okay. Remember this? We have discussed before. You are given vector OA, OB, OC, OD. Show that find the value. Show that for any value of x, ABCD is a parallelogram. So if I calculate AB and I calculate DC, because must be parallel, right? So this is AB, this is DC. So you see, they are the same, exactly the same. So since AB and DC are the same, this one same direction, same length, same. So definitely another pair also will be the same. Therefore, it is a parallelogram. And it is free from x, you see, no more x. So no matter what is your x, your ABCD is parallelogram. Remember, this is part A that we have discussed. All right. So now we are going to see part B. Okay, so what is part B? Determine the value of x for which ABCD is a rectangle. Okay, so I show like this lah. This is part A that we have discussed. Now part B. This is part B. This is part B. This is part A. Okay. So now we want it to be rectangle. ABCD is a rectangle. So rectangle means perpendicular. Okay. Okay. So I'm going to use AB and BC lah. Okay. From part A, AB I have calculate. -6, -6. I have calculate. So I use. Then I have to calculate BC lah. Because these are not suitable anymore. I calculate BC. So BC is OC minus OB. OC, OB. So I get this. This is your BC. All right. So if it is rectangle, so definitely AB and BC perpendicular. So if these two vectors are perpendicular, then AB dot BC will be 0, no? Scalar product. So this is AB, this is BC. So dot -6 multiplied x plus 2. This one multiplied this one. All right. So 6x equals 6, your x equals 1. So when x equals 1, or for this position vector, if x equals 1, then ABCD become rectangle. Okay? Okay, next will be the last question for today. All right, question 6, STPM 2011. Okay, the position vector of three non-collinear, they are not collinear, BCD, relative to O are BCD, small letter BCD respectively. And you are given B dot C minus D equals 0 and C dot D minus P also equals 0. So these two information given to you. Show that BC is perpendicular to OD. BC perpendicular to OD. So again, if I want to show BC perpendicular to OD, I must find these two vectors and I must show that their scalar product is equal 0, right? Okay, BC and OD, Okay, so BC. So BC, OC minus OB lah. So means OC is C lah. OB is B. OD is D lah. Okay, so I want to show their scalar product. BC dot OD. So BC dot OD. Alright, by using distributive law. So C dot D minus B dot D. Alright, so I stop here for a while. Okay, it seems like from here nothing can continue, right? But don't forget the information given to us. Alright, so the first information given to us is B dot C minus D equals 0. So I using distributive law, I expand B dot C minus B dot D. So I get B dot C same as B dot D. B dot C same as B dot D. I name it as equation 1. Then the second information given to us is this one, C dot D minus B equals 0. So distributive, right? Expand C dot D minus C dot B. So shift minus C dot B to this side. So I get C dot D same as C dot B. And we know that commutative, right? So C dot B same as B dot C lah. Okay? So C dot D same as B dot C. Second equation. Yeah, I know this question a lot of BBDD. So listen carefully. Alright, now I'm going to sub 1 and 2 into this one. Just now what is C dot D? C dot D is B dot C, right? So C dot D is same as B dot C. What is B dot D? B dot D same as B dot C. So B dot D same as B dot C also. So B dot C minus B dot C, 0. Okay? So the scalar product for C minus B dot D equals 0. Therefore, I can make conclusion that vector C minus B perpendicular to vector D. And what is C minus B? BC lah. So BC perpendicular to OD. Okay? So I have discussed so many examples. So suppose no problem. Alright? So right after finish your video, please complete these 3 questions as quiz. Alright? I think you have about another 45 minutes. No, like 40 minutes. Okay? You have about another 40 minutes. So enough for you to complete this quick question. So I want to see all these I want to see the solution of all these 3 questions upload to the folder by 10:30. Alright? Please don't delay. By 10:30, I want to see everyone upload these 3 questions to the Google Drive. Okay? And this is your homework. So checkpoint 6.2, do all the questions that I haven't discussed. And in the notes, only one question too, just now remember? So complete all this lah. So the afternoon slot. Okay? The afternoon slot, 2 o'clock to 3 o'clock. Please complete your homework. Okay? Alright. Thank you, class.